Lecture 4. Let's just recap where we got to. Maybe do a big recap in some sense. We spent most of our time to date, well, we still will, looking at decision-making models. And in both cases, whether we're looking at search, or whether we're looking at planning, which we did for the second lecture and into the third, and then planning under uncertainty, which we did in the third and we'll carry on today. I didn't make a big thing about it, but it's now maybe important to reflect that there are two key elements to every planning system. We have the model, which we use to represent the robot's world and the robot's actions, okay? And we have the algorithm that takes that model and produces a plan or a policy. And we've been teaching you that the reason it's important to sort of start separating these is because we've typically paired an algorithm and a model, or an algorithm and a representation together, but it's useful as you think about these things, and we'll do this particularly today, to be able to think about different algorithms that operate on the same model. And we saw that a little bit, right? We saw search. So we had our model for the planning problems that we're solving by search. The model was simply a state transition system. We had states and actions, and we didn't think too much about how we modeled those explicitly, but we had states and actions, and then we had different algorithms we could run on that transition system. We had A star, depth first search, breadth first search. Okay, those were different algorithms that we'd run on the same model. We then moved on to classical planning. And in classical planning, we saw a very particular type of model, the STRIPS model or PDDL model. And that model was, again, a state transition model. We had states and actions, but we had a kind of a more elaborate representation that allowed us to compactly represent the deterministic transitions from one state to a next, using actions that expressed transitions that could apply to any state that satisfied the preconditions of that action. So we could have an action that talked about flying a plane from one location to another. And as long as we had planes and airports, we could apply that action to any combination of planes and airports. So that was just still a state action system. And we had the representation, this time it was PDDL. And then we had algorithms. We looked at forward search, we looked at backward search, and we looked at algorithms that we could apply to any model formatted or constructed using PDDL. We looked at ways of creating heuristics. Now, the key, if you remember, the key problem with, or not problem, the key difficulty in applying PDDL or STRIPS models to robotics is that they are deterministic. So that, if you remember, that meant the successor state, so the next state we see in a problem, is always fully determined by the previous state and the action we applied. That's why it's deterministic. We can always, in our model, we always know what the next state will be after we apply an action. But in reality, when our robots are acting in the world, the next state is not always fully determined simply by the action and the previous state. Often we want to think about the next state arriving probabilistically using a distribution or a probability distribution over the possible state. And so that led us to almost the last model that we'll see in this course, which is a Markov decision process. So a Markov decision process is really only a slight extension of the previous class of models we saw. In the previous class of models, we had a state, we had an action, and then we transitioned to a new state. The MDP has a state and an action, and then a probability distribution over the states that would be reached from that action. And whilst that only feels like a small addition, adding a probability distribution, that small addition changes the problem setup completely. Because we now need to have different algorithms to reason over the models. And we even had a different solution concept. So when we were planning in deterministic models, our solution was a plan, a sequence of actions. Sometimes you'd call it a straight line plan, because it's simply a sequence of actions. In the non-deterministic problems, we had to move to having a policy. The policy is a mapping or a lookup table that takes you from any state to an action choice. And that policy could be stationary and deterministic, which means it only depends on the previous state, but that's only the action choice, not the outcome. Or it could have history, or it could be stochastic. But in general, we're going to think of a policy as taking us from a single state to telling us what action we should apply. But it says nothing about what state will be reached after that action. That's why we have the policy. We were in an action, we're in a state, we apply an action, and then we just repeat that loop because we don't know what state we're going to end up in exactly. So that's the recap. And the important thing, the reason I'm doing this recap is because today and the next lecture, we're going to look at a range of different algorithms that operate on Markov decision processes. And they're going to have different properties, and you would choose them in different situations. But this lecture, the next lecture, I'd say are kind of core to what my research is. And I think more at the forefront of the way people think about planning in robots today. Okay. Any questions?
Actually, really quick question.
Yeah.
So for indeterministic in PDDL, is it enough, or do we need other source to supplement?
For what? So what problem would you be solving?
So in the situations that requires indeterministic.
Like non-deterministic, do you mean?
Yeah, sorry, yeah, indeterministic or non-deterministic, yeah.
Well, there you wouldn't use PDDL.
Oh, okay.
Because PDDL only expresses deterministic domains.
Okay.
So there's a version of PDDL called probabilistic PDDL, and there's another one called RDDL, which both express non-deterministic domains. So you can kind of inherit properties of PDDL in other domains.
Okay. Thank you.
But we don't. But like the PDDL we've seen so far only has one outcome or one effect.
Yeah. Yeah.
Okay.
Makes more sense.
Cool. Good question. Any other questions? Okay. Right. So this is the recap of the Markov decision process. When we think about this, we're going to use all these capital letters refer to sets or functions, or tuples in this case. So M is the model or the Markov decision process. We have our state space that we had before. We've got our actions. So S and A, we've seen in everything we've done. We also have goal states. So in fact, most of this is the same as all the search problems and all the planning problems, right? We have states and actions. We're going to have costs for our actions. We have goal states that we're trying to reach. The only difference is we have this T in the middle, which is a transition function, which gives us our probabilistic model. And this particular version of an MDP, we're going to look at almost exclusively something called a stochastic shortest path problem, or an SSP. And this, we look at this because this is sort of the closest analog to a planning or search problem that we've seen. It's the shortest path problem, i.e. we're trying to minimize the cost to get to a goal, which is exactly what we did in the Pokemon domain, and it's typically what we do in planning as well, in classical planning. But it's stochastic, which means there's randomness in it, or uncertainty. And just as a reminder, we can think about it a bit like this. So we're going to think about navigation problems. And a navigation problem, we might have a few locations or nodes, and our action might look like this. So the action would be to drive from node 1 to node 2. And then there might be some probability of getting that action. So the key thing here actually is to see that the action only really goes up to here. So you can think about that bit as the action. You see that little blob there. So that's our action. And then after that blob, we have the outcomes. So with probability 0.85, we reach N2. Probability 0.1, we reach N3. And probability 0.05, we might reach some failure state. That failure state may not correspond to a physical location. It may be the robot being stuck somewhere and needing help. And then we can express these transitions as a transition function, which gives the probabilities. And in this case, our cost will always be positive numbers. They don't have to be integers, but they will be positive numbers. And what we want to do is minimize the cost to achieve a particular outcome. And I've said this a few times, it's worth repeating. All of the examples I'll use are really focused on navigation because it's just simpler to understand that. But in practice, our states would typically be factored. So this is exactly, well, not exactly, very similar to the PDDL setup. So our state internally might have more structure than we're looking at here. So it might have a set of locations that could contain other things. It might have a failure flag. It might have a battery level. All of these things, it might have time. Okay, so our states internally could be more complicated. But for now, we're only going to think about location because that's just a bit easy. And in fact, as Pedong mentioned PDDL to start with, you can express all of this using PDDL, except for the effects. It's just the effects that would be probabilistic. So you could have a precondition over a factored state representation, and you could reason about when those actions are applicable. It's just the effects would be expressed in a different form. Okay, so that's the model, right? The model looks like this. This is just one action. For a planning problem for robots, we then have lots and lots of actions like this, okay? So now we're going to look at the first algorithm that we're going to use to create a policy for a Markov decision process. And the idea of that policy is to solve the stochastic shortest path problem. So this policy is going to be a solution to the planning problem, and in general, it's going to be a solution to the stochastic shortest path problem, which is the type of planning problem we're looking at. And in some sense, this is the most important sort of couple of slides for the next two lectures, because this is going to give us the maths that we need to understand how all these algorithms work. And the maths is based on something called the Bellman equations, or the Bellman optimality equations. All right? So that's the key takeaway from these slides, the Bellman equations. The algorithm we're going to look at is something called value iteration. But that's just one algorithm. Many different algorithms we'll see all use the Bellman equations somehow. So when we solve an MDP, we want to find the optimal policy. Optimal means the best policy. And the optimal policy will give us the action A to take in state S, which minimizes the cost to reach the goal. So that's what we're looking for. We're looking to construct a policy where for every state, the policy gives us the minimum cost action. And that minimum cost action isn't the minimum cost in the current state, it's the minimum cost to reach the goal. So we're going to express that cost using something called a Q value. And the Q value is sometimes also called the cost to go. So it's the cost to go from that state via the action to the goal. And there's a couple of important things here that we'll just go through slowly. So the cost to go is the expected cost of executing action A and then following the optimal policy afterwards. Okay. There's three things here, and we'll go through these in turn. Expected cost. In fact, we'll just look at expected cost and then optimal policy. So, can someone remind the class what it means to take the expectation of a probability distribution, or the expected value of a probability distribution over some random variable? Okay, you're all taking a while to warm up. Oh, Peidong, you unmuted. I saw at least one unmute.
Yeah, I was thinking about, are you talking about the path cost plus the heuristic value?
No, this is we're in a different space now. So any random variable can have an expectation. So if I had a, let's say, a random variable which would be a coin toss, and that coin could be heads or tails. And what I might do is I might express that as a 1 or a 0. Okay? So we can think about a coin toss, and my coin, if I get heads, I score 1. And if I get tails, I score 0. Now, the expected cost is, you can think of it as like the average value that I get back, or the average score that I get back over an infinite run of coin tosses. So I would express my probability of the coin as a probability distribution. Let's assume it's a fair coin. Okay, so I've got my C is the random variable. P gives us the probability of the outcomes. And so then I can talk about the expected value, so E, let's just change color. I can talk about the expected value of C. And that is the probability of heads times heads plus the probability of tails times tails, which equals, well, probability of heads is 0.5 times 1 plus 0.5 times 0. So the expected value of the coin is 0.5. Okay. So the expectation is like an average of all of the outcomes of a random variable weighted by those probabilities. So the key bit of maths here really is this bit. We take each probability and we multiply it by the value.
So Professor, here it's also like, say, now if I randomly toss a coin, either heads or tails, but because it will only have two events, possible two events, either head, either tail. Now, because we assume that the coin is a valid coin in the sense two sides are same. I mean, it doesn't have any distortion. So if we really toss it for many times, eventually, so for showing up each side, either heads or tail, that would be 0.5. So expected value is just the average of all the possible outcomes. I mean, that's my understanding.
Yes.
So like if I extend this, like if I have a cubic will have 6 sides. So in that case, the expected value should be 16%, a little over 16%, is it?
No, that's the probability of getting a side.
But here is the same thing, because if we toss a coin many times, an infinite number of times, then heads and tails is we get still 5%. So here is the average is 5%,
yes,
0.5.
The key thing here is we're assuming the probabilities, right? We know the probabilities.
Yeah.
These are the probabilities.
Yeah.
And we can call these the values.
Okay.
And E is the expected value. Okay?
Yeah.
So we actually care about the value we get back, not the probability.
Oh, okay.
So in this case, what we've done is we valued a head at 1 and a tail at 0. So it just so happens that the expected value is the same as the probability of getting either side.
Ah, okay.
If we did this in a dice, right, we would have the value of 1 with a probability of 1 over 6, the value of 2 with the probability of 1 over 6, the value of 3. Let's assume we've got a 3-sided dice, which is impossible, but there we go.
Yeah.
Then the expected value would be 1 times a third plus 2 times a third plus 3 times a third.
Oh, okay, I got it. So here we see that we assign a value either to heads or tails, because over here, like we are taking the value from dice, like 1, 2, 3, 4. But in general, heads or tails, I mean, they don't have any value assigned on any side. But here we are doing it.
Yes, exactly.
Okay. Yeah.
So this is 5 over 3, right? That's the kind of makes sense, right? It's the average, a third of the total value. No, 6 over 3. Got that. I'm rubbish. There we go. 6 over 3, which equals 2. So the average score from that dice is 2. Sometimes you get a 1, sometimes you get a 3, sometimes you get a 2. But on average, the value you'd expect overall, the average value of all your rolls will be 2. Gotcha. But that's the key idea. The key thing that was a bit strange in the heads and tails example is that we assigned a value to a head and a value to a tail. Any other questions about this? This is a really important concept to understand. So I'm happy to go through this again.
No, here we are doing assigning value like heads or tails, 1 or 0. So this 1 is the max value, or it has any, I mean, like constraint?
No, just think about it as an arbitrary betting game.
Oh, okay.
So if I toss a coin, I give you one value. Sorry, if I toss a coin and it comes heads, I give you one value. And if I toss it and you get tails, I give you another value. Doesn't matter.
Okay.
I can assign any value I want to that. I would just have to change the math that I was doing.
Okay, right. Now it makes sense for the dice. Otherwise, I was thinking it was a little weird. So it's arbitrary value.
Yeah, they're just arbitrary values. Any other questions on expected value? So actually, let's reinforce this. I'm going to just stop that. Add a blank slide. It's a bit easier to draw over the blank slides. So let's imagine we've got a, jumping around. Let's imagine now we've got a planning problem. And it's going to be a slightly weird one. But let's say we've got 3 routes to reach our goal. Okay, so our goal is here. And then we've got these intermediate states. We'll call this 1, no. We'll call this A, B, and C. And in A, B, and C, there's only one action you can take. So there's an action here. Each state has one action that gets you to the goal with probability 1. Okay? But each action has a different cost. If I'm in state A, this action costs 1. If I'm in state B, this action costs 2. And if I'm in state 3, the action costs 3. For whatever reason. Okay? And now, sorry. Trying to not cancel the screen. So over here, I'll be in an initial state, which we'll call I. And again, I've only got one action. And this action, for now, is going to cost 0. So 0 cost action. But it has 3 outcomes. Okay. This one is going to be 0.1. This is going to be 0.7. And this is going to be 0.2. Right. So we're going to label these actions. This is just going to be action A. No, that's a silly thing. This is going to be P, Q, R, S. But what the question we were talking about was the expected, when we were talking about Q values, what we're interested in is the Q value of some action, say P, in state I. So, before I carry on, I want you to take 30 seconds to think about how you would work out the expected cost of executing action P. The key thing to note here is there's no choice, right? It's a sort of silly example, but I'm going to execute action P, and then I'm going to reach either A, B, or C with some probability. And then when I reach A, B, or C, all I can do is execute the one action that's there to get me to my goal. So the question I'm going to ask someone to tell me in about 20 seconds is to explain how you would calculate, or how you think you would calculate, the expected cost of action P. Well, I'm also happy to take a question or two if someone doesn't understand the example. Okay, right, someone stick their hand up and I will choose. I want ideally a few hands to choose from. Stick your hand up if you want to have a go at telling me how you would calculate the expected cost of action P?
Here.
Cool. Okay.
I think the expected cost is the probability of the action of the states to go to A, B, and C times the cost from A, B, and C to the goal. So that will be 0.1 times 1 plus 0.7 times 2 plus 0.2 times 3.
Yeah, perfect. Thank you very much, Jeremy. 2 times 3, which equals something. Okay, I'm not going to work that out.
That's 2.1.
Cool.
Yeah, 2.1.
Okay, there you go. So that's perfect, right? So what we've done is we've thought about the expected cost of that action. And you can see that it actually involves two costs. So there's something missing from this, which is actually a slightly silly thing, but it's actually 0 plus this. Because if I change this number here, there's also a cost for the action, that action. So if I made that 7, I'd have to make that 7, and then this would equal 9.1. So Jeremy's answer was correct, but we also need to factor in that 0, which was a slightly tricky thing. I left it out, but there we go. Okay, so I've made this example easy by removing any choice after A, B, or C. So we only there's no choice in this problem. All we can do is use the probabilities we've got. But this is a good start. Has anyone got any questions about this before we go on? Okay. Right. So if we go back here, get back to our so what we're going to do is we want to calculate the expected cost to first execute action A in state S, and that we've seen. But the difficult bit is that we also want to then follow an optimal policy to our goal. Because we need to look at the cost of the whole path, or the expected cost of the whole path. And that's what our Q value does. So here we've got our Q value, and the star up here means it's optimal. So here we're assuming we're going to calculate the optimal cost. And the function has 3 things. It has the cost of the action SA, so in this case, in our previous example, this was the one that was either 0 or 7. That's the cost of the first action. And we then have the value of the remaining state, of the state we reach. And we sum that up and multiply it by the probability of reaching that state. So in our previous example, we had the transition probability of, we were in state I, we performed action P, and we reached state A. And we multiplied that by the cost of performing that action, which was 0, plus the value of being in A, which I think we wrote as 1. Because the value of being A is the cost of being in A, the optimal cost of reaching the goal. And we did that for A, B, and C. And so you can decompose this to think about the way we did before. So this has introduced something new. What we got in this slide that we didn't have before is this idea of the value of a state. So the value of a state is a function that reports how good is it to be in that state. Right? That's the way to think about the value of a state. How good is that state? Well, a state is only as good as the policy that gets you to the goal from that state. Okay, so a state is only as good as your ability to reach the goal from that state. So that's the value. The value is of a state is the expected cost to reach the goal from that state. And because we're looking at the optimal Q value, we're going to assume that we follow the optimal policy from that goal. And we're going to define this in a minute. Okay? In fact, let's define it and then we can come back and talk. So the question is, how do we define this optimal value function? Well, the optimal value function is simply the minimum cost action, the Q value of the minimum cost action to reach the goal. So that says, well, if we're already in the goal, then the cost is 0. Otherwise, the value of the state, we think back to what I just said, the value of the state is how good it is to be in that state. And how good it is to be in that state is related to the cost to reach the goal from that state, because that's all we care about. So therefore, the value of a state is the minimum cost, expected cost action Q value. So what we're doing here is we're minimizing over A. So there's a secret little A. So if you've done minimization, we're choosing A from our set of actions, and we're choosing the one that minimizes the Q value of that action in that state. Right, anybody got questions? We'll go through a worked example in a minute so you can see how this works.
Sorry, Nick, I'm quite curious. For the transition probability, is this always given, or do we set it up manually in a real world situation?
It's a good question. So there are kind of 3 ways we can think about this. In a kind of toy problem like this, it might be given to you if we know in advance. For example, if we're writing an MDP for a game where there's a dice, we might know that probability exactly at the start. What we might do is have some ability to look at past data. And so for a lot of our robot problems, we compute these probabilities or calculate these probabilities by looking at prior data. And so we might say, my robot has taken this action 1,000,000 times, and I can then look at those 1,000,000 data points and calculate the probability of particular outcomes. Or we might say, you know what, I don't know the probability at all, and all I can do is act in the world. In which case, we're never given T, and we have to calculate it as we act. And that is what a reinforcement learning problem is. So a planning problem, we are given our MDP, including transition functions, and we create policies using that. If we're not given our transition function, then it's a reinforcement learning problem, and we have to do something slightly different. And that's next lecture, or the lecture after, depending on how we make progress. So that's the key difference between reinforcement learning and planning in MDPs. In planning, we're given T, either by hand or from data, and in reinforcement learning, we're not given T. And we may not have access to C either. But...
Okay, thank you.
All right. Any other questions about Q and V? We're going to see Q and V a lot in the next couple of lectures. Okay, let's move on to an example, or showing how it works. So, well, actually, back to this. Get rid of all that. There's clearly a problem here. If you were going to write this down mathematically or as a software, you can see that I want to, so let's just sort of step back through the process. I want to create a policy. I want to build algorithms that create policies. We create policies by determining the best action to take in a state. And we do that by calculating Q values. But in order to calculate a Q value, we need a V value. But to get our V values, we need a Q value. So there is a recursive relationship or a reciprocal relationship between these two things. I can't calculate Q without V, and I can't calculate V without Q. And that's where the value iteration algorithm comes in. Here what we do is we use something called dynamic programming. So dynamic programming is kind of a mathematical formulation that allows you to successively approximate a value using a previous estimate of the value. So dynamic programming looks like this. What we're going to do is we're going to use it to calculate the value of states. And the key thing here is now our value is parameterized by this subscript n, which is going to be the iteration number, where iteration means loop. Right? So if I had a for loop, every time I go through that for loop, it's an iteration. Or a repeat loop or a while loop, that's an iteration. So the idea here is we use the values at n-1 to calculate the value at iteration n. And so we're going to have this sequence where we calculate all the values and then move on to the next iteration and reuse those values from the previous loop. And the question is, what do we do, well, when n equals 0? Well, when n equals 0, we're going to just do some arbitrary initialization. So we need to start with a guess, and then we can improve that guess as we go. And at the end, well, we need two extra things that we'll look at. We need a stopping condition. So when do we stop doing this? And then how do we compute a policy? And we'll look at each of these. So the stopping condition, we look at something called the residual. So the residual is the difference between the value of every state between two iterations. So that's this bit. Okay, so we compute the residual, which is the difference in the values between two iterations. And then we stop when that difference is smaller than some epsilon, some constant. So that's where we look for convergence. And then our policy is simply the minimum cost Q value for each state. Right, let's do this in practice. So we're going to use an example that this is an example we'll use repeatedly for the next lecture, this lecture and next. And it's a smaller example than some of the ones we've seen, but it allows us to look quite carefully at the values. So here we've got another grid world, and we've got rooms A, B, C, D, E, and F, and we've got doors between the rooms. And there are two types of doors. There are kind of doors that are always open, or gaps, and doors that actually have some kind of blockage in them. Now, the door with the gap, if I drive through there, or I try and drive through there, it costs me 1. If I try and drive through the other type of door, it costs me 2. Okay, so it's more expensive to try and go through a door with an actual door there. And if I go through a gap, I have probability 1 of reaching the other side. If I try and go through a doorway, I have probability D of trying to reach the other side, and probability 1 minus D, I stay in the previous state. So if we look at the example here, if the probability of being in state A, given that I'm in D and I move up, equals 0.9, and the probability that I'll be in state D, given that I'm in D and I go up, equals 0.1. Okay, so that's basically, we're looking at this action. And this is our transition function for being in state D and applying up. Okay, so this is the example we'll use. And our goal is to be in C. Okay, our goal is to reach C. And so we're going to solve a stochastic shortest path problem to get to C. Excuse me, any questions about the example? Okay. So, we can write this down in 2 ways, and this isn't super important, but it's been one of the things over the years that has confused people. And it kind of relates to the question of how you model these things. We can think about this in a way that sort of corresponds to classical planning or PDDL. So we can think about it as an agent-based model where we have 4 actions, up, down, left, and right. And if we do that, we can kind of write down a conditional probability table for each action. So here, I would write down a probability table for the up action. And it tells me the transition probability I would executing up in every state. So you can see here there's state S, here there's state S prime, and I can see that I've got, if I'm in A, B, or C, right, these top 3, if I execute up, nothing happens. I stay in that state. If I'm in state D and I go up, well, there's probability 0.9 that I reach A, or there's probably 0.1 I stay in D. So one of the reasons I'm saying this is because in the rest of the slides, to fit everything in, I kind of took a shortcut when I was writing the slides, which means it's not quite formally correct, but hopefully easier to understand. So the up, if we're talking about the up action in D, I simply skip the success, the action, and just write the high probability outcome state. Okay, so that's the same as saying actually it's Q, D, up. Or I'd be writing T, D, up, A, for example. And of course, if I was writing this problem formally, I'd need this times 4. I'd need to write down all the probabilities. And this is a bit different from what we saw when I was just doing a single action. This is encoding the entire problem, and it shows you all the probabilities we need. I could also think about this more like the mobile robot example. And if you remember with that mobile robot example, all we did was think about individual edges in a graph. And so I could do that instead, and I could think about the edges. And then I would write a table like this for every edge. But the slightly weird thing is for most of these edges, they're kind of useless, right? All of these things are useless because I only ever think about that edge when I'm in state F. Sorry. So it depends on the type of problem and algorithm. One of these things may be more efficient. And the reason to think about this is it's also easier to sort of map it to the Q value. So the QDA in this case would correspond to the edge of taking DA. All right. So let's look at how value iteration works. We're going to start by initializing our costs. So we said that in iteration, in the first iteration, when n equals 0, we have to do some kind of arbitrary initialization. And the key idea here is because we are minimizing costs, we initialize high, and the algorithm will bring down these things down. So you can initialize, a sort of safe initialization is to initialize to the maximum possible cost for any action in your problem. Sorry, the maximum possible value for any action in your problem. And rather than calculate that, I've gone with 100 because it's a nice round number. And what you see in the table is a list of both state values, so V's, and state action values, Q's. And as you remember, the V's are calculated from the Q's by just taking the min over them. So, what do we do in iteration 1? Well, for every cell in this graph, we need to calculate a value in this table. So, for example, for Q in iteration 1, we're going to calculate the FC. So we're in iteration 1, we're calculating the cost to go. We add in the action cost, right? So in this case, the action cost of F to C, I can't see that bit of my slide. F to C, the cost is 2. We add in the outcome probability of getting to C, which is up here, which is 0.9, and the outcome probability of staying in that state. And we multiply the outcome value, so this is just the expectation that we did before, and then we do it for both states. But the key thing here is when we use these outcome values, we're calculating at iteration 1, and we're reading in the values from iteration 0, the previous iteration. So that gives us a value of 12. And I can do the same for the other action in state F. And then I can compute the value of F by taking the minimum over those two actions. Any questions about that? This is about it, really, in terms of the difficulty.
Excuse me, Nick, where is this 2 coming from? Sorry. For iteration, like iteration equal 2 plus 0.9.
So if you look at the line above, this tells you where we're filling it in. So that corresponds to that. That corresponds to that, and that corresponds to that.
Yes.
So where is that?
Yeah.
So what is the 2?
Yeah. What is this 2? That was my question.
You tell me.
I mean, I'm lost. If I knew, I wouldn't ask you.
Okay. And does anyone else want to tell me what the 2 stands for, or where we got the 2?
Yeah. 2 is a cost from F to C because the door is just like it's not a gap, so it costs it 2.
Yeah. So the C here is the action cost.
Okay.
The action is the action of going from F, of trying to go from F to C. And in our previous example,
all right. Okay, got it.
Yeah. So our previous example, in this domain, we said that if there's a door, it's going to cost us 2 to try, and if there's a gap, it's going to cost us 1.
Oh, right.
So we're looking at the action F to C, which is trying to go up from F. So that's a door, so that's 2.
Okay, thank you.
Cool. Any other questions?
Sorry.
Yep.
Yeah, the door is one way, so the cost of, for example, the C to F is inexistent.
Yeah, there's no action that takes us from C to F directly.
Okay, thank you.
So we just don't have that option. But perhaps the important thing in this calculation is when we try that door from F to C, there are 2 possible outcomes. Either we get to C or we stay in F, right? So there's 2 outcomes that we anticipate, and we calculate the cost using both of those outcomes.
But in this case, like CFC, so the cost of action 2 is arbitrarily defined, is it?
Which one, sorry?
CFC equal to that one, action cost.
Yes. That's not arbitrarily defined. That's defined by our domain model.
Oh, okay.
In some sense, it is arbitrary, but we can't pick it. It's given to us by the world.
Oh, okay. I mean, okay, got it. Thank you.
These are great questions. Anyone else? Okay.